Okay, so going through the Maxwell-Boltzmann equation again. So I have this equation here. At the beginning, I have all these terms together, but they're just constants. So I can just treat them as constants. And then I have this v squared term, and then this exponential term, which is equal to v squared as well. So I'm going to break this down into different sections and hopefully explain to you what's going on. The important thing is we were asked to find the most probable speed of the particles. Now, the Maxwell-Boltzmann distribution has this shape here. And the most probable speed of my particles, I'm measuring the probability that they have a particular speed on the y-axis and the speed of the particles on the x-axis. And so my most probable speed is when I have this turning point here. I have this turning point here, so the gradient at this turning point is equal to 0. So what I need to do is I need to differentiate my function and set it equal to 0. And then I'll find the different values that have a solution when my differential equals 0. And one of those will be this turning point up here. Okay, so this is my equation for my Maxwell-Boltzmann distribution. And I know that at my turning point, the differential of this is going to be equal to 0. So what I need to do is differentiate this function with respect to v. So I'm differentiating everything here with respect to v, my one variable. Everything in here that isn't a v is just a constant. And I know there's a lot of constants flying around, but they are just there as a constant. So I've got two things going on here. This is just all a constant, so just for the minute I'm just going to ignore this. I end up with one function multiplied by another function. That means I'm going to need to use the product rule. The product rule is one function multiplied by another function. So here I'm going to rename this here and call this one A, and I'm going to rename this one here and call this one B. So A is equal to v squared, and therefore dA by dV is equal to 2v. Now I've got B is equal to e to the minus mv squared over 2RT, and so I need to differentiate B with respect to v. But this time I'm going to need to use the chain rule. Here I've got a function of a function, which is the chain rule. So here I'm going to say this here, I'm going to call a new variable. I'm going to call this C. So v squared is equal to C. And so now I'm going to differentiate my C here with respect to B. So dC by dV is equal to 2v, and if I replace this as c in here, dB multiplied by dC is equal to, so this is e to the minus mc over 2RT. This is just e to the minus ax. It's the same thing. So this just becomes all of these constants minus m over 2RT e to the minus, and I've got this c, but I'm going to replace this straight away with my v squared over 2RT multiplied by the m there as well. So now together these two make the chain rule. So overall dB by dV is equal to this one multiplied by this one. So this makes this minus 2mv over 2RT e to the minus mv squared over 2RT. And I can cancel these twos if I want to. Okay, so now I have, this is my original equation, and I've just written down my product rule here to be clear exactly what I'm using. So my differential that I want, my fancy function here, differentiated with respect to v, the velocity, is equal to A, dB by dV, plus B, dA by dV. And I've just written out all of those things that we've just had on that previous sheet. So now I just need to fill it in. And the one thing I need to remember as well is at the moment I'm not working with this constant. I'm going to throw that in right at the end. So A is equal to V squared multiplied by dB by dV, which is equal to minus 2 mV over 2 RT, e to the minus mV squared over 2 RT. And now I need to have plus B, which is just this e to the minus mV squared over 2 RT. And then I need to multiply that by my dA by dt, which is just 2V. And then all of that just gets multiplied by my constant. So I'm just going to write this answer out in full, including this constant term at the beginning, which is 4 pi into m over 2 pi RT to the 3 over 2. And I'm going to just do a little bit of rearranging as I do this, just to group all of my terms together. So this is into 2v e to the minus mv squared over 2rt minus 2mv v squared over 2rt e to the minus mv squared over 2rt. Now here we can see that we've got some common terms. This here, this exponential term is a common term, but so is 2v. So I'm just going to take all of those terms out into the front. So this is equal to 4 pi m over 2 pi rt to the 3 over 2. And then I'm just going to take all of these terms out. So this is 2v e to the minus mv squared over 2rt. And if I take this out of here, I end up with 1. And if I take this lot out of here, I end up with this being minus v squared m over 2rt. Okay. So what I have now is I have my differentiated equation here, and I know that this is equal to 0 at a turning point. So I can just take these terms separately and say where they're going to equal 0. So here I could have the term V. So I have the potential of V is equal to 0. That's one of my turning points, because if I say here V is equal to 0, this makes this whole thing be equal to 0, regardless of what any of the other numbers are. So V is equal to 0 is one of my solutions to this. I also have the solution that e to the minus mv squared over 2rt is a solution. So e to the minus mv squared over 2rt is equal to 0. Again, that is one of my solutions. And my final solution is this one here, which is 1 minus mv squared over 2rt is equal to 0. So the reason it's these three is I need to have a term with a velocity in it, a v in it. That's my only variable. And so that's the only thing I can change in order for this to be 0. And if I go right the way back to the beginning, we can see that actually when v is equal to 0, this is this turning point down here. When I have this solution here, e to the minus mv squared, this is the solution that's right the way off at infinity, so it's all the way out of here. I've got a turning point. And my final solution, this 1 minus mv squared over 2rt, it must be this one here. So what I'm going to do is just simply rearrange this So just a simple bit of rearrangement, mv squared over 2RT is equal to 1, or v squared is equal to 2RT over m, or v is equal to the square root of 2RT over m. And that is my most probable velocity. So I've done this. I started off with this Maxwell-Boltzmann distribution with this equation here. I've differentiated it once using a combination of the product and the chain rules, and I have come out with my differential being this great big function here. And then I've set this function to be 0, and then I've looked at where all of my v's are, because it's my v's that are providing the solutions to my Maxwell-Boltzmann distribution. So I have a solution at v is equal to 0, that's one turning point. The solution when the velocity is infinite, that's another turning point. And I have a solution here when I have 1 minus mv squared over 2RT is equal to 0. This is the solution that I care about. It's the only kind of rational value. It's a real value. It's not either infinite or 0. So this is the one I care about. I hope this video was instructive and informative. If you've still got some questions about the Maxwell distribution, please drop me an email. Thank you.